Turbulence Modeling. Throughout this chapter, we assume constant density and viscosity and no thermal interaction. For our assumption in this chapter, we can write no viscosity, no constant density, constant velocity, and no thermal interaction. So that only the continuity and momentum equations are to be solved for velocity and pressure. For continuity, we have run U on run X, run V on run Y, and momentum rho dV on dt We will not work with the differential energy relation in this chapter, but it is very important both for heat transfer calculation and for general understanding of the duct flow process. There is work being done by pressure forces to drive the flow throughout the duct. Where does this energy go exactly? There is no work done by the shear stress because the velocity at the wall is zero. The answer is the pressure work is balanced by viscous dissipation in the interior of the flow. The integral of dissipation balanced by dissipation function phi, as we said before, over the flow field will be equal to the pressure work. Both laminar and turbulent flow satisfy the equations of the momentum. For laminar flow, where there are no random fluctuations, we go right to the attack and solve them for a variety of geometries, leaving many more, of course, for the problems. Reynolds time average concept is a basic concept for the turbulence modeling. For turbulence, let me write Reynolds time averaging concept. For turbulent flow, because of the fluctuation, every velocity and pressure term in the continued momentum equation is a rapidly varying random function of time and space. At present, our mathematics cannot be handled such instantaneous fluctuation variables. No single pair of random functions for V, E, and P as vectors. We have V equals to Vx and t, and also we have P, a function of x and t. Is now to be a solution to the equation of momentum. Moreover, our attention to an engineer is toward to the average of mean values of velocity, pressure, shear stress, and the lag in high Reynolds number flow. This approach led observed Reynolds in 19th century Therefore, rewrite the equation of momentum in terms of mean or time average turbulent variable mean or time average variable. The time mean u of a turbulent function is equals to u dt, where t is an averaging period taken to the longer than any significant period of the fluctuation themselves. Let me write it an averaging period taken to be longer than any significant period of fluctuation themselves. The mean values of turbulent velocity and pressure are illustrated in the for turbulent gas and water flow, an averaging period t equals to 5 seconds is usually quite adequate. T equals to 5 seconds for the turbulent gas and water flow. The fluctuation u prime is defined as deviation of u from its averaging values. We have a definition: deviation of u from its average value. Also shown in the picture also. By definition, that a fluctuation has zero mean value is u prime. Let me write the u prime first is the deviation of velocity from its average, and we can calculate the u prime bar, mean value of u prime or u prime bar equals to the relation u minus u bar dt equals to u bar minus u bar, which is equals to 0. So the mean value of the fluctuation deviation of u prime is 0. However, the mean square of fluctuation is not 0 and is a measure of intensity of turbulence. So we can write a relation for intensity of turbulence. U prime 2 bar dt is not equal to 0. Nor in general all the mean fluctuation products such as u prime bar and 0 in a typical turbulent flow. Reynolds' idea was to split each property into mean plus fluctuating variables. So we have the relation for the velocity component, which is the mean value of velocity plus the deviation of velocity from its mean value, and for other direction we have also same relation. W equals to and P equals to P prime. With definition of this mean value, we can replace into the momentum equation and we can obtain this relation in next page. Let me add some pages first. So for continuity, with replacing the average definition of velocities due to the average and deviation of the average quantities, we can obtain for continuity and we have thus we have the relation for thus the deviation parts are 0. We can obtain for continuity and for the relation of momentum replacing to the continuity equation, we can obtain these relations for example x direction, the pressure average gradient plus the force due to the gravity and the force due to the viscosity. U prime W prime. This is the relation for momentum equation in turbulent flow. The three correlation terms in the dissipation rate formulation is, for example, this and These relations are called turbulent stresses. So let me write and rho u prime v prime and rho u prime w prime turbulent stresses they have the same dimension as accurate right alongside the Newton stress term. This relation and so on. Actually, they are convective acceleration terms, which while the density appears, not stresses. So they are the convective acceleration terms and not stresses. Let me write here in one page, not stresses, but they have the mathematical effect of stress and are so thermal almost universally in the literature. The turbulent stresses are known a priori and must be related by experimental to geometry and flow conditions. In dark boundary layer flow, the stress of turbulent stress associated with the direction y normal to the wall in dominant, and we can approximate with excellent accuracy a simpler string-wise momentum equation as below, as this relation rho material derivation or total derivation of u. Total derivation is temporal and plus rho jx plus rho tau on y curve when tau is equals to the mu round u bar on round y minus round u prime v prime where the first one is the laminar turbulence laminar plus the turbulence, the shear stress due to the turbulence. This figure shows the typical velocity and shear distribution in turbulent flow near wall. Shear and velocity shown in this picture. This figure shows the distribution of the shear stress in laminar flow. Let me in laminar flow here and turbulent flow as shown in this picture. From typical measurement across a turbulent shear layer near a wall, laminar shear is dominant near the wall and turbulent shear dominates in the outer layer. There is an intermediate region called the overlap layer, where both laminar and turbulent shear are important. These three regions are labeled in the picture. The overlap in this picture shown with dashed point line, overlap of laminar flow and turbulent regime. In the outer layer, shear stress of turbulent is 2 or 3 order of magnitude greater than tau laminar, and vice versa in the wall layer. This experimental fact enables us to use a crude but very effective model for the velocity distribution across a turbulent wall layer, the logarithmic overlap law. The next this different subsection in this, the logarithmic overlap law, we have in this picture. We have seen, let me write, the logarithmic overlap law. We have seen in this picture that there are 3 regions in turbulent flow near a wall. The first one is wall layer, viscous shear dominates. Second, outer layer, turbulent shear dominates. And 3 is overlap layer. Both types of shear are important. From now on, let us agree to drop the over bar from velocity u bar. Let tau be the wall shear stress and delta and u represent the thickness and the, let me write here, shear stress. Delta and u represent the thickness and velocity. And the edge of outer layer is for the wall layer. Prandtl deduces that u must be independent of the shear stress, so shear thickness layer, we have the relation for a function of u wall shear stress rho and y. With the bidimensional analysis, this equivalent to be obtained u plus and u star equals to the this equation is called the law of the wall. And quantity u star equal the friction velocity because it has dimension of, although it is not actually a flow velocity. Sequentially, in the 1933 relation deduces that U is in the outer layer is independent of the molecular viscosity, but its deviation from the stream velocity U must depend on the layer thickness delta as we defined before, and the other properties such as wall shear stress and density. So we can write for relation a function of delta rho and y. So with the non-dimensionalize of this function, we can obtain this relation for non-dimensional applications, where U star has the same meaning as the before equation. Is called the velocity defect law for the outer layer. For the outer both the wall and the defect law are found to be accurate for a wide variety of experimental turbulent ducts and boundary layer flows. They are different in form, yet they must be overlapped smoothly in the intermediate layer. In the previous B, Silicon showed that this can be true only if the overlap layer velocity varies logarithmically with y with the relation of plus b overlap layer. Over the far range of turbulent smooth wall flows, the dimensionless constant k and b are found to have the approximate values. K approximately is equals to the 4100 and b is 5. Is called the logarithmic overlap layer. Let me write logarithmic overlap layer. Thus, by dimensional reasoning and physical insight, we infer that a plot of U versus L and Y in a turbulent shear layer will show a curved wall region, a curved outer region, and a straight line logarithmic overlap. This figure shows that the logarithmic overlap diagrams for This figure shows that the experimental verification of inner and outer and overlap layer laws relating velocities profile in turbulent wall flow. In this picture, exactly shows that this is exactly the case. The four outer law profiles shown all merge smoothly with the logarithmic overlap law, but have different magnitude because they vary in external pressure gradient. The wall law is unique and follows the linear viscous relation. So we have this relation from this diagram y plus from the wall to about y plus equals to 5. Thereafter, curving over the mesh with the logarithmic law at about y plus equals to 30. Believe it or not, this picture, which is nothing more than a shred collection of velocity profile, is the basis for most existing theory of turbulent shear flows. Notice that we have not solved any equation at all but have merely expressed the streamwise velocity in a neat form. There is a serendipity in this picture. The logarithmic law, instead of just being a short overlapping link, actually approximates nearly the entire velocity profile, except for outer law when the pressure is increasing strolling downstream. The inner wall law typically extends over less than 2% of the profile and can be neglected. Thus, we can use the equation of logarithmic overlap layer, is shown here, as an excellent approximation to solve nearly every turbulent flow problem presented in this and the next chapter. Many additional applications are also available in various references. Advanced modeling concept. The next section is, let me write here, modeling concept. Turbulence modeling is a very active field. Scores of papers have been published to more accurately simulate the turbulence stresses and their y and z component. This research, now available in advanced texts, goes well beyond the present book, which is confined to the use of the logarithmic law. For pipe and boundary layer problems, for example, Prandtl, who invented boundary layer theory, later proposed an eddy viscosity model for the Reynolds stress term. Is the equation for, we have the viscosity of turbulence due to turbulence equals to rho L2, the absolute of on dy. The term ut, which is the property of the flow, not the fluid. If you write the properties of a flow, not the fluid, and is called the eddy viscosity. And can be modeled in various ways. The model popular, where L is called the mixing length, of the turbulent eddies. Near a solid wall, L is approximately proportional to distance from the wall and suggested as L equals to where K equals to the constant as said before, as a relation for advancing modeling concept. There are some solved problems related to the turbulence modeling section, especially for the equation of overlap, logarithmic overlap layer.